Okay, I have started the recording, and you think that it is Thursday, 27th of February, but the reality is that it's never happened this night when I prepared the slides, and I tell you. Well, okay, I'm just kidding. So I want to tell you what I could not tell you yesterday. So this will be more a lecture than a practice. I talked about different definition of matrices, and determinants and everything. But there are special matrices. Some of them was mentioned. The first was the diagonal matrices. These are very simple. There are only elements in the main diagonal. The operations, multiplications, are very, very simple with them. So you know that already because I have told you. There are some theorems how to calculate the invert, how to do this power, multiplication, everything, that's fine. Now we can switch to snakes and permutation matrices. These matrices are the result of permutation. Permutation of rows of diagonal matrices. Well, this is very fundamental. You can make a permutation with switching element pairs. So, for example, this so this permutation, this 2, 4, 3, 1 can be reached switching the twice the first and second, and the second and fourth rows. So the start here is the identical matrix. That's fine. You have a vector quite large, and then you switch the first and the second row. Then you got this. Then you switch the new second row and the fourth row. Wait a minute. Yes, you do. And you got this matrix, and it's P like permutation. What is the meaning of this? The next one is this. You have this permutation matrix that you just constructed, and you have an appropriate other matrix. It's not a square matrix. Its indexes are fine, and now you switch the rows with this matrix multiplication. That's permutation. Okay, wait. This is something not right. Something is not right. Oh, Oh. Well, okay, I must apologize, but something error was made. So partly of this, the slides were not translated from Hungarian to English. I will give you the appropriate stuff, but I don't know what happened. Actually, I know. I used ChatGPT to translate some part of these slides, and it didn't translate some part of this. Apology. This will be English on the Teams. This is bad. This is very bad. This is very bad. Okay. Sorry, this is unexpected. So, which is worse? Well, which is better? To use Hungarian slides or translate the slides before you right now? Translated? Should I? Is it better or?
It depends on how sure you are that you know all the English.
I know all English stuff because not the English is important. So, not English is the important stuff. Okay, I do something else. A third thing, which is also very bad. I will translate here and I will do the sorry. Okay, let's do it. here I set this, and you can follow what I do, and really sorry. Okay, so snakes, they really bite. So if you do permutation for using this method, you create from diagonal matrices, and then you create a new matrix. Those matrices called snakes or transversals. If you create a snake from an identity matrix, then it's called permutation matrix. And here are the examples. Okay, so these are snakes and the last two are permutation matrices. Okay, so very briefly, the permutation matrices has only one element in each row and each column. The snake is a square matrix and it has only one non-zero element in each column and each row. All threads could be get from diagonal matrix by switching columns. And here there is a mistake. There are many mistakes, but it's principal. This is 0, not 9. I will go back. Sorry. Okay. Are you familiar in LaTeX? Because now you will. So you can get a snake from diagonal matrix if you also permutate the columns. Usually these statements and theses are symmetric for rows and columns. And if P permutation matrix, you can get the PA from A with the same permutation of the rows. That permutation leads of the rows, that permutation leads to A from P. I mean the well, I demonstrated. So you change the rows in the A matrix and also in this identity matrix. Usually I don't use ChatGPT to translate the Hungarian text to English, and very often I have English text first and not Hungarian. The ChatGPT doesn't know the right terms, not always, at least. Okay, what's the problem with this? An example for the effective way of doing your job. Well, okay, so this is, at least go close to English. Let's start. sorry. So permutation matrices, you start from diagonal matrices and you can switch the rows, or you can start from the from an identity matrix and switch the rows. Then you can construct so-called permutation matrix, and calculating an other matrix, multiplying with another matrix, then you got something special. Yeah, yesterday I mentioned the functionals. That's very strange functions because they argument our function. But here it's also the argument is a function. Doesn't matter. So the definition for the permutation matrix and snakes. The matrices created by permutation from diagonal matrices are called snakes or transversals. Snakes created from identity matrix are called permutation matrix. The difference is that in permutation in snakes you have in snakes and permutation matrices you have only one element in each row and each column which is non-zero. If that element is 1, then we are talking about permutation matrices. These are very useful in a way. So I wanted to tell you these special matrices. I don't know, 2 weeks ago, right after the transformation matrices. You had the transformation. It's parallel shifting, rotation, and other things. So this is one thing that use matrices. Okay, then you can, yeah, I told you. So if P is a permutation matrix and you can get the PA from A by the same permutation of the rows, that permutation leads to P from the eigen identity matrix. Actually, yes, to get this, we switched the first and the second row, and then the second and the fourth row. Okay, let's see this. Let's switch the first and the second row. Then, if we switch the first and the second row, then the second row will be on the top. Then switch the new second row and the old fourth row. Then you got this. And this is really the same how you construct the permutation matrix. Okay. So if so the product of any two permutation matrices has the same size, and it's also a permutation matrix. That was the same for diagonal matrices. The product of diagonal matrices was also a diagonal matrix. The inverse of a permutation is equal to its transpose. So if P is a permutation matrix, then its inverse is its transpose. Okay, actually, let's deduct this, but yeah. If P and Q are two permutation matrices, then the row vectors of their product is this P I Q, and PIQ is a standard unit vector. And the only element in the column is 1, and there is only one such column. In the other columns are 0. So if you do this product of the permutation matrix and its transpose, then the diagonal element is given from this. This P is one column, and the only non-zero element is 1. And if you do this operation, then got this, and this is the transpose this is the not the transpose, so this is the eigen operator. Okay, this is one example. You have this permutation matrix. You do the transpose, and when you do the operation, then you got the identity matrix. Okay, which is important from here, not this deduction and everything, which is quite mess, that if you do the inversion, then you go the transpose. So you will never do of the permutation matrix. You never do the inversion of the permutation matrix. You do the transpose, and that's the inverse. Okay, this is end of the mess. I mean the ChatGPT translated stuff. We have talked about triangular matrices. This matrix is a matrix which has no element above or below of the main diagonal. It's upper triangular if there is no element below the main diagonal, and it's lower triangular if there is no non-zero element above the main diagonal. And if you have the only one in the main diagonal, then it's a unit triangular matrix. Remember, the triangular matrix and trapezoid matrix is good because you can calculate the determinant just multiplying the elements in the main diagonal. Okay, so all sum, product, and inverse of an upper triangular matrix are also an upper triangular matrix, and it's the same for the lower triangular matrix. And the triangular matrix is invertible if none of the diagonal elements are 0. Yes, the one condition of the inversion is to have a determinant which is non-zero. The triangular matrix determinant is the multiplication of all elements in the main diagonal. So if there is only one, then the determinant is 0, then there is no inversion. Okay. Very, very interesting. These skew symmetric matrices. It's very, very weird, because I remember when I learned this, it was called antisymmetric matrices. A square matrix is symmetric if it's identical to its transpose. So if you check the matrix A, then it's a symmetric matrix, because if you check the main diagonal, then it's symmetric for the main diagonal, or I can say that I can transpose and I got the same matrix. If everything goes well, then very soon we will talk about again eigenvalue problems, and there will be some thesis and statements, the eigenvalues of these type of matrices, symmetric matrices. So this subject is so very often I repeat, which was in the elementary linear algebra. The reason is that I don't remember, I don't know, for example, so what do you remember about elementary algebra? That's one thing. And the other thing, there are some overlap in the syllabus. I try to do it shortly, but the meaning of this subject is to learn new theses and the new methods. The real problem is that you should do it with programming. Many things would be more interesting with using Python or something like this. But that's not the case. When I had the Python course last semester, then I tried to use examples from the elementary linear algebra, but it didn't lead anywhere. So finally I did something else. Doesn't matter. This is the symmetric when the transpose of the matrix is the same than the original matrix. If the transpose of the matrix is not the same but not the opposite, so it's cooperative -1, then because we talk about skew symmetric matrices. It's very, very weird. I remember exactly that was the antisymmetric matrices. Perhaps it's the Hungarian term, but the Hungarian term is not that one. The Hungarian term is something stripped matrix or tilted matrix. Weird. So the second is as an example, because if you check this, you do the transpose, then the elements are the opposite on the same side, or on the different side of the main diagonal. Also, I would need a pointer or something like this. Actually, I have one. Okay. There is something interesting. Wait a little bit. If you have these skew symmetric matrices, then the main diagonal has only 0 elements. Great. 1. Okay. Then. Okay. Oh, that's interesting. it's okay. It works just weird. Yes. So A is a symmetric matrix, B is skew symmetric, and the C is just an ordinary matrix. Okay, and the next comment is, I just told you about the element in the main diagonal is 0 for a skew symmetric matrix. For the symmetric and skew symmetric matrices, the sum, the scalar product, then the inverse of the skews this is where again okay, not weird, just perhaps I'm a bit paranoid. Okay, so that's the same, almost the same sentence twice. So for the symmetric and the skew symmetric matrices, sum, scalar product, and inverse. The sum, scalar product, and inverse of the symmetric and skew symmetric matrices are also symmetric and skew symmetric, respectively. Which is more important is this decomposition of any matrix to a symmetric and skew symmetric matrix. Every square matrix can be divided into symmetric and skew symmetric matrix. The sum of the symmetric and skew symmetric matrix. In this way, you calculate the transpose, and then this first term is the symmetric, and this is the skew symmetric term. And the deduction of this is quite simple. You start from the other side. This is what we want to check. This is one term from it, and to be a symmetric, it must be its transpose must be the same. So I transpose this. The transpose of a sum is the transpose of the elements. So this is the original matrix, and then it's commutative, so I can, the matrix sum, then I got the same, so this is symmetric. Great. I have to prove that this part is skew symmetric. Skew symmetric means this must be, the transpose of this must be minus this. Okay, I start from this, I do the transpose again, I have this one and I have this one, and if I find this minus, then I got the minus one of this. So this is skew symmetric. So this is the symmetric part, this is the skew symmetric part. In the original formula, you have this. So you start from this. This is a half A, another half A here, a half transpose A is here, minus here, so the result is the original E. So this is what I wanted to demonstrate. It's great. If you have these products, I mean the product of the transpose of any matrix and the matrix, or the matrix and the transpose, so it's product from left and right, then these are symmetric for, okay, let's start from here. To understand this, you should remember for this, it was after the inversion. So if you have a product and you do the transpose of the product, then that is the transpose of the second element multiplied with transpose of the first element. Let's go back. Okay, I am here. I want to prove that this is symmetric. If this is symmetric, then the transpose of this is the same. What I should do, I have a transpose of a product, so that will be the transpose of the second element, then the transpose of the first element. Transpose is the same, this is transpose, so I'm ready. If I do this one, then I have to, oh, there is an extra E. Fortunately, I have the source code. Here. No, here. Okay, so now I start from this A transpose multiplied by A. I do the transpose and I have to get the same. It's almost trivial. I start with the second. This is the transpose of the second because this is a product. And then this is the transpose of the first. Transpose is of course, it's the original. So I got the same. I wanted to prove this one. Great. This is about the matrices, and this subject would be about this. Last time I talked about matrix inversion. You know very well what is matrix inversion, but not this is the important thing. The important, and not this method is important, but this Sherman-Morrison-Woodbury theorem. Okay, very, very interesting, this theorem, because it's not a theorem, it's called formula. And actually, this formula is deducted from something else, and which is very good. There is a bibliography, and this formula is not any of the suggested book and notes. Even in my notes, I didn't find it, so I have to hunt this down from the internet, which is weird, actually, a little bit. The meaning of this is interesting. There are a bunch of methods that makes your life easy. They help you to calculate faster and easier with less operation, a determinant, a matrix product, an inversion of the matrix. So these are mostly numerical methods. Will you learn numerical analysis? I think not. Not. Okay. Additional very interesting things. I will have the same course after yours from noon, and I should teach them something perfectly different. Fortunately, one of my tasks to change the syllabus, so that will be the same. But perhaps I have told you this. Okay, let's start from this Sherman-Morrison formula. You have an invertible square matrix A, n times m. And you have two vectors, and these vectors has n component and elements. There is a restriction. That's actually should be an eigenvector. The transpose of this vector and the inversion of the matrix so this production is not zero. Then this A plus UV transpose is invertible, and you can calculate it with this operation. Well, when you should do it manually, that's ugly. But if you do with computers, then you got some minutes or seconds. We learned the Gauss elimination for determinants. Also, we learned the same method for the system of linear equations. These are nice for students, and these are nice in a test. If you have small matrices and a small number of linear equations, 10, then that's okay. If you have 100 or 1000, that's not okay. That's an experience actually. Yeah, with my brother, my professor, that was one of the homework. If you use that method, and then it's costly. I many times mentioned you this order thing. There is an algorithm, and you add a parameter with n element. And if you double the number of the elements, it's very important whether the algorithm, the elapsed time of doing the algorithm, terminating the calculations is double, square double, I mean 4 times, or exponential, or factorial, or something like this. That's called ordo. And the Gauss elimination is very bad. This Sherman-Morrison formula is better. I cannot tell you the ordo because it was not described, and it's something very difficult, but it's better. From this Sherman-Morrison formula, you can deduct the Woodbury formula. This is the only place, I mean the syllabus, where it is called Sherman-Morrison-Woodbury formula. It's usually only Woodbury formula. If you have an inverse of this rank K correction of a matrix, then you can compute using the inverse of the original matrix with rank K correction. Very nice. So what does it mean? It means that you have this U and W, and this U and W has a special parameters, and you multiply the matrix with it. That's the Rank correction. And if you have this term, you can calculate faster to calculate the inverse of the A, and then calculate this stuff, and then you reach the nirvana and the paradise or whatever you want. I don't deduct this because its deduction is very long. So I don't expect you to learn because even I didn't do it. And this matrices has a special size. A matrix A has n times n, and the others is n times key times key and key times m, because you can do this multiplication in this way. If you check this properly, and C is the eigen, the identity matrix, then you can see the same or almost the same like above. Okay, that was in the syllabus, so I told you. I fulfilled my duty, but sorry for the mess and this bad translation. Yes, and this formula helps you solve faster the system of linear equations, and the tool, the way is calculate faster matrix inverses. So now, this is the end of the lecture of yesterday. Now in the next 4 minutes, the practice comes. I started this early disk stuff. Well, I thought it's simple. It is not simple at all. At least it's interesting. This is somehow the early disk. It's not nice. And this is this reach 1, and which is difficult to do any operation with sinus xperics. I started to, that yesterday with the Hungarians, I started to do the derivation to find the points where it's not inversion, so it's where it has a local maximum minima. And but finally find that this first disk, this one, is at approximately 0.13. So I constructed a special operation I don't know. And it's not ready. I will look in it properly and fix it. This is supposed to be a matrix transformation, the special red heart operation or whatever. So if you use this matrix operation, then you got in theory only this, and everywhere else it will be 0. In theory, I don't know, I haven't finished, but I finished now the practice, and sorry for the mess, sorry for being late. This was such a week, sorry. Thank you very much.